So let's explore the 13.8 billion year history of our universe in 15 minutes. So I'll have to talk fast. We saw that as we explored farther and farther out into space, the farther we looked, the more stuff we found. Very intuitive. But finally, beyond all these beautiful galaxies, we saw that the edge of what we could see, the edge of this spherical region that we call our universe, from the sphere from which light has had time to reach us during the 13.8 billion years since our Big Bang, is this strange radiation coming with these strange yellow, blue, and green colorations here. What is that? How can we understand this? So let's think more about our place in time. Fortunately, we can learn a lot about our place in time just from looking into the sky, because the sky is like a time machine. When I look at you, I see you the way you were about 6 nanoseconds ago. When I look at the sun, I see the sun the way it was 8 minutes ago. And when I look at some of these galaxies here in the Hubble Ultra Deep Field, I see them the way they were 10 billion years ago. So what have we learned by observing the universe at various stages of its cosmic history? We have learned something really, really surprising. And to make you fully appreciate just how surprising it is, I want you for a moment to pretend that each one of you is a galaxy. And I'm looking at you with my telescope. And I see something really strange. I see that those of you near me here are in your 90s. Looking good, but in your 90s. And you guys are in your 80s, you're in your 70s, you're in your 60s, 50s, 40s. Here's a bunch of teenagers over there, and then a bunch of toddlers. And in the second last rows there, some infants. And the very last row, at the back of the room there, is completely empty. Why on earth did you guys decide to sort yourself by age when you filtered into the classroom? And compounding my confusion, the rear wall of the classroom is glowing at me with a strange microwave glow. And as if that weren't weird enough, you're all blushing. You guys near the front are just a little bit pink in the face. You guys near the back are like seriously tomato red. So what's going on here? Is it something I said? Well, we can understand this exactly because the farther away I look, right, the farther into the past I'm seeing. So when I look at nearby galaxies from my vantage point over here, I see them the way they were pretty recently, when they had had time to mature and become big and modern looking. When I look farther into the past, I'm seeing galaxies long ago that hadn't had time yet to grow up and become big galaxies. And really far away, all I see is baby galaxies that had not had time to do much growing at all. And beyond that, corresponding to the very last row here in the classroom, I see no galaxies at all, because I'm looking so far back in time that I'm witnessing the epoch before there were any galaxies that had time to form. All I'm seeing there is the raw material out of which the galaxies later formed, namely hydrogen gas, which looks black here because it's transparent. What's with the blushing? Why do you all look red in the face? Well, if you go down to the highway, you hear the cars go, ew, ew, ew. That's the Doppler effect, right? Something receding from you has a lower frequency. Cars do not sound, ew. They go, ew. Lower frequency when they're going away. And it's exactly the same way, not just with sound, but with light. So a galaxy flying away will have its light shifted to lower frequencies, which here corresponds to colors towards the red. So we call this redshift in astronomy. The more redshifted something is, the faster it's flying away. And Edwin Hubble discovered that pretty much all the galaxies he looked at were redshifted. Everything seemed to be flying away from us. And this is what we mean when we say that our universe is expanding. Now, if a galaxy is flying away from here, how long ago was it near us? That's the same question, basically, as if you have a bank robber driving away from a bank with some velocity v, a distance d from the bank. We can figure out this when the crime happened, basically by just taking the distance and dividing it by the velocity, and then correcting for acceleration and deceleration, right? We can play the exact same game with these galaxies and say that take the distance divided by the velocity, that tells us how long ago something rather dramatic happened where this galaxy was kind of over here. And what Edwin Hubble discovered when he made these fantastic measurements in the late 1920s was that things weren't expanding just in some random haphazard way, but in a very organized way. Pretty much all the galaxies were moving effectively straight away from Earth. Much like what you would see if you were looking from the vantage point of a chocolate chip in a muffin that was rising in the oven. You would see all the other chocolate chips moving straight away from you. And moreover, the farther away they were, the faster they receded. If they were 5 times as far away, they receded 5 times as fast. So the velocity of recession for a galaxy was simply equal to the distance to it times this constant, which Hubble got named after him. We now call it the Hubble constant, or the Hubble parameter. Now, if we combine that with a bank robber analogy and simply ask, okay, how long ago was a particular galaxy here, right? If we take the distance divided by the speed, but the speed is given by Hubble's formula above here. So let's plug that in. Distance divided by Hubble's constant times distance. Now we can cancel out the distance, and we get the same answer for every single galaxy, regardless of how far away it is. And when you plug in the numbers here, it gives you about 14 billion years. When we do this a little more accurately to take into account acceleration and deceleration, we get 13.8 billion years. So what this is saying is that about 13.8 billion years ago, something really crazy happened, because pretty much everything was on top of everything else. Things were extremely dense. Okay? In other words, we've been witnessing now an expansion very much like what happens in the oven when you bake. Everything is receding from everything else in this very orderly fashion, where the patterns stay the same. It's just that all distances keep getting increased by the same factor. That also gives you an alternative way of thinking about the expanding universe that some of you might find more intuitive. Instead of thinking about a static space where these galaxies are flying apart like this, you can think of all these galaxies actually just sitting still in a space that's just expanding, because the relative patterns are all the same. Suppose we look at these rulers and we just relabel all the millimeters into centimeters, and then we change the centimeters into meters and so on. Now all distances have increased by the same factor. That's what we mean when we say that space is expanding. And it's allowed to do that, according to Einstein's general relativity theory. Now, another one of the really surprising things we've discovered about the history of our universe from looking out, when I look at you galaxies here, was that the far wall was glowing with microwaves. Why would it do that? Well, since everything is expanding, so is the gas that fills space, right? We all know that if you expand the gas, it will cool off. That's how air conditioners and refrigerators work. So if we've run this backwards, and imagine going backward in time, the gas is getting more and more compressed, which means it's getting hotter and hotter and hotter. And when a gas, if you heat up a liquid, it turns into gas, steam. If you heat up a gas, what does it turn into eventually? A plasma, that's right. That's exactly right. So eventually, beyond all of these galaxies, we're going to see a plasma screen of hydrogen plasma. And that's opaque. So it's going to look to us like there's an opaque wall there of plasma. And it's going to look that way in whatever direction I choose to look. I'm going to see galaxies, and I'm going to see nothing, and then there's going to be a plasma screen. So it looks to us actually like we're surrounded by a spherical plasma screen that we're looking at from inside. And we can, and we in fact have, photographed this with these beautiful, and gotten these beautiful images from the Wilkinson microwave anisotropy probe. And in fact, Maya, do you have our universe? Can you pass it around to the audience? So you can be gentle and loving with our universe. It's treated us pretty well so far. These are remarkable pictures of these are baby pictures of what our universe looked like just 400,000 years after our Big Bang. 13.8 billion years it took the light to reach us here. Okay? Did they get it right? Well, last year, the Planck satellite released even better images of this, going from 3 megapixels to 50 megapixels. And yes, look how well they agree. It's just fantastic. except now it's an even sharper image. It's really spectacular that we've been able to get this sort of images. These are photos of the most distant thing you can photograph in science. Now, another striking thing about these images is they reveal that the baby universe was very boring, because the color scale here has been stretched by 5 or by 10 to the 5 for you to even see anything. It would look gray otherwise, or uniform. What's shown here is simply how hot the plasma screen is in different places. And it differs by only 1,000% from place to place, which means that the plasma was only 1,000% denser in some places than other places. That's about as uniform as the air in this room. I mean, raise your hand if you can hear me. That's because there are sound waves propagating here, right? So the density is different in different places. And if I speak about this loud, it varies by about 1,000%, about a foot from my mouth. So this is how boring our universe was early on, like the air here. How did it get so interesting? How did you get these clumps like stars and planets in the World Science Festival? Well, because over time, in addition to this process of expansion that we've now talked a great deal about, that you can see in this supercomputer simulation, there was also a separate process of clustering that transformed the boring into interesting. And we can see this better with another supercomputer simulation here, where I've removed the expansion so you can focus on the transition from smooth and dull to clumpy and interesting. It's hundreds of millions of light years on the side here, and gradually it gets more and more interesting. Why? Because if you have a little bit more stuff over here than in its surroundings, then the gravitational pull from that will draw in more stuff, and you get a bigger clump, which is even more able now to draw in more matter from the surroundings. You get a still bigger clump, and before you know it, you form clumps about the size of galaxies. So imagine a galaxy forming in each one of these halos or clumps that are seen in this picture. Let's zoom in a lot here now and take a look at how you can form a solar system. We have, again, same thing happening on a smaller scale. We have a cloud of gas. Gravity, again, is trying to squish it together, make it even clumpier, but it's spinning, so it can't clump it into a point. That would violate the so-called conservation of angular momentum. Instead, it squishes it down into a pizza shape, disk. But in the center, it keeps getting denser and denser and hotter until the gas gets so hot that nuclear fusion ensues and a star is born. And in the meantime, stuff in the outer parts of this disk has formed planets, which become revealed when the nascent star blows away the disk out of which it was formed. And it's no surprise that all of the planets are orbiting around our sun in the same sense, which is also the same sense in which the sun itself is rotating roughly once a month, because all of this spin, all of this angular momentum came from that initial cloud. So that's a very short version of how the World Science Festival got here. So to summarize, we have seen that during the past 13.8 billion years, there were two quite different processes that went on. There was the process of expansion, which transformed our universe from small to big, from hot to cold, from dense to more rarefied. But in parallel with that, there was also this transition from smooth and uniform and boring to clumpy and interesting. And it's interesting that the different forces of nature have actually taken turns tag teaming, driving this clustering. The strong interaction early on clumped together triplets of quarks that form protons and neutrons, and then bound together these protons and neutrons into atomic nuclei. Then the electric force took over, took the lead, and started clumping together nuclei with electrons to form atoms, and then handed over the baton to the gravitational force, which clumped enormous numbers of atoms into stars, 10 to the 57 atoms or so in a typical star, and also formed planets, and ultimately people, and the World Science Festival. Now, although we understand quite well then what happened during the past 13.8 billion years, what happened before this? Why did we start out with all this hot stuff flying apart in this very orderly and boring way? That's what we're going to turn to next.